Hi, this is Kenny Lee, and let's take a look at kinetic energy. Unlike potential energy, where there was all different forms of potential energy, kinetic energy only comes in one variety, and that's motion. You have to be moving to have kinetic energy. And this is our basic equation. Kinetic energy, I still use Ke for kinetic energy, equals 1/2 the mass times velocity squared. Or sometimes they just simplify it and just use 1 capital K to mean kinetic energy. Now I said half the mass. Well, really it's half this mass velocity squared. Either way, you should get the same answer. So, energy is measured in joules, just like work and potential energy. And 1 joule equals 1 kilogram meter squared over second squared. And you can see that with this equation a lot easier. Velocity is in meters per second, and you square it, so you'll have meters squared over second squared, then times the mass, times kilograms. And so we get that unit. But we prefer to just use the abbreviation joules to make things a little bit easier. Let's take a look at this problem. We've got a 600 kilogram car traveling at 40 meters per second. We want to know its kinetic energy. Well, it's actually quite simple. Kinetic energy is equal to 1/2 mv squared. So in this case, mass is 600. Velocity is 40. And it's only the velocity that's squared. So I'll take half of 600, which is 300. 40 squared is 1600. And we multiply those together, and we get 1600 times 300 gives us a big whopping 480,000 joules of kinetic energy. You are going to get large amounts of energy. Don't let that throw you off. If you get a big number, that probably means you did it right, because if we use anything close to actual numbers of life-size objects, and not just like small matchbox cars, but actual real cars, we're going to get a large amount of energy. So if you get a big number, don't let that scare you. You probably did fine. Let's see what happens if we have to find out something else besides the kinetic energy. So in this first one, we've got a bike. It is traveling 15 meters per second. It has a kinetic energy of 6,700 joules, but I want to know the mass of the bike. Well, we can take care of that with the kinetic energy equation. We'll just have to solve for m. Now I'm going to go ahead and plug in the numbers that I know. That's 6750 half m. We don't know what m is, but velocity is 15, and that's squared. Well, we can do the math on this side. And so 15 squared, remember your order of operations, and then divide by 2, because I want to take half of that, gives me 6750 equals 112.5 m. It doesn't matter that the m was in the middle, we still can multiply those together. Then we just need to take the 6,750 and divide by 112.5, and we get a mass of 60 kilograms for that bike. That's not too bad, but a lot of times what we really want to do is find the velocity if we happen to know the energy. So for this one, we've got a 12 kilogram cart traveling at a constant velocity. That's good. If it has 937.5 joules of kinetic energy, what's its velocity? Well, since we know kinetic energy, we can always start off with this, and hopefully it'll lead us on the right path. I've got 937.5 joules. Mass is 12, and I got to find velocity. Well, go ahead and do the math you can do. Half of 12 is 6. And now we can actually do this division. 937.5 divided by 6 gives me 156.25 but that's v squared, not the velocity. So we still got one more step to do. We have to take the square root. And so when we do, we find the velocity to be 12.5 meters per second for that cart. Again, pretty much a plug and chug type problem, but you have to make sure that you remember to take the square root. Those problems are all well and good, but what happens if we get something like this? Which of the following would give us the greatest increase in kinetic energy? And we've actually got three different situations. Keep the mass the same but triple the velocity. Keep the velocity the same but quadruple the mass. Triple the mass and double the velocity at the same time. Which one of those would give us the biggest increase? A lot of times we call this proportional reasoning. And one way that we can work this out is by first getting a baseline. And what I mean by a baseline is that start off with the basic equation. Kinetic energy is 1/2 mv squared. And then ignore any constants. Like we're going to pretend the half doesn't exist. And replace everything over here with ones. So kinetic energy is 1 times 1 squared, which is just 1. That's our baseline that we're going to use to compare with. So for this first one, we keep the mass the same but triple the velocity. We're going to again take 1/2 mv squared. Again, don't worry about the constant. We want to keep the mass the same, so we're going to leave it 1, but we're going to triple the velocity. But remember, that's squared. 3 squared is 9 times another 1 is still 9. So the kinetic energy would have gone up by a factor of 9. In the red zone here, we want to keep velocity the same, but quadruple the mass. So again, start off with the basic equation, 1/2 mv squared. Forget about the constant. We're going to we're going to quadruple the mass, but leave velocity the same, so it stays a 1. Well, 1 squared is 1 times 4 gives us a kinetic energy of 4. So it will increase by 4 times the original amount. For the green one, again, always start off with your equation. That's your guide to thinking. Get rid of the constant. The mass is tripled, and the velocity is doubled. But remember, that's squared. So the kinetic energy will increase by 12 times as much. So this will actually give us the biggest increase, followed by that, and that does the least. Since velocity is squared, it's going to have a bigger impact than changing the mass. Let's say that we had a situation where the original kinetic energy was 5 joules. That was my original kinetic energy. So if we did this, then my new kinetic energy would be 5 times 9, so 45 joules. If this is what we did to it, that was the original kinetic energy, so now 5 times 4, I have 20 joules of kinetic energy. And on this last one, if again, the original situation had 5 joules, but we did this to it, now we'll multiply those and we get 60 joules. So again, the biggest, middle, least. All right. Thank you. On the next video, we'll talk about the work energy theorem.